The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
At this time, I'd like to introduce Neil Hawkins, our last presenter for today.
Good afternoon, people. I'm a professor emeritus at the University of Illinois, and I've been involved with floating bridges in detail for some 30 years now. Most recent experience was looking at some new construction of a floating bridge in Seattle, which sort of has gone a bit wrong. And my co-presenter in this is Mint Lewin, who is the director of the Office of Bridge Technology of the FHWA, and he was the Washington State Design Bridge Engineer for the existing LACEY v. MURROW Bridge, which is the bridge we're going to talk about today. Floating bridges have been around for quite a long time. The Romans used floating bridges, Napoleon used floating bridges in many of his battles, and here is one from the Civil War, a floating bridge over the James River in Richmond, Virginia. And of course, one of our most famous floating bridges is the bridge across the Golden Horn in Istanbul, Turkey. It was first built in the 1800s, but has now been replaced with a bascule steel bridge. But I keep on suggesting to the Washington State Department of Transportation that they could solve some of their funding problems if they just allow the construction of restaurants in the space between the pontoons and the fly-top bridge. Now, around the world, there are some 16 different floating bridges, which are concrete. And I want to point these out, that in the United States, the main ones are in Washington State. There is one up at Kelowna in British Columbia, and there is another one over in Pearl City in Honolulu. There are some famous, more recent ones in Norway, and you may have seen an article in Concrete Briefs today talking about a new one they're going to build in Norway, and which will be a combination of a bridge and a tunnel. So this advances all the time. Now, I'm going to sort of change pace, but this is a significant factor. There are concrete ships. Most people sort of know that there have been concrete ships, but they always come along during a war when we lose a lot of steel. So instead, we start to do is, hey, can't we build in concrete? So in World War I, we built 12 concrete ships. And there's the SS Palo Alto. And I give the dimensions: 419 feet long, 54 feet wide, and 35 feet deep. Just carry those dimensions in your head. In World War II, we had 24 ships. And as a graduate of the University of Illinois, most of you will know something there called Talbot Lab, which is where the first concrete experiments were done. And there's the SSS Arthur Newell Talbot, named after the same person, 336 feet long, 54 feet wide, and 35 feet deep. If you want to look more at concrete ships, go to the URL, concrete ships, and you'll find a history of every one of these concrete ships and where there may be remains or still floating. So, if you could build concrete ships, why not build concrete floating bridges? And that's what happened in Seattle. The world's first concrete floating bridge opened in Seattle in July 2, 1940, and there's a picture of it. Why Why build a concrete floating bridge? Seattle had a problem. And I really appreciate the last speaker because she talked about Spokane. And what we had to do was somehow or other get from Seattle through the mountains, which are the Cascade Mountains, and there's a pass there of about 3,000 feet. But the rest of the mountains are 8,000 feet, and Mount Rainier is 14,000 feet, and it's pretty difficult. So that was a one pass. And also the city was expanding. You can see the dark block of the city, but the best area for it to occupy was on the other side of the lake, Lake Washington there, which is about 40 miles long and something up to 5 miles wide. So the question was, why not build a bridge across the lake? But there were a few challenges. First, the depth of the lake and the soils. The lake is a fjord, and it's 200 feet deep, and after you get through the 200 feet of water, you get 200 feet of soft soils in many places, particularly near the banks. Second, the place had to remain open to shipping, and there was a limit of 10,000 tons on the ship, and we'll see this a little bit further on. That's because the Corps of Engineers had built some locks to protect Lake Washington from salt water. Lake Washington is fresh, Puget Sound is salt water, and that size would only take 10,000 ships, 10,000 ton ships, so theirs was something. But then, of course, you had this problem of winds can develop, and there's a fetch to this site of about 10 miles, and for that, the maximum winds blowing from the southeast could create waves up to 9 feet in height. So that's a challenge. All right, along came an innovator, and his name was Homer Hadley. And speaking at ASCE meeting when he was 36 in 1921, he proposed that they build concrete ships connected together to produce this bridge. He'd worked in the Philadelphia shipyards building those concrete ships in World War I. His proposal was for a bridge made of interconnected concrete barges. Homer became the PCA's Northwest Regional Engineer late in 1921 and continued to push the concrete bridge concept as a private toll bridge from 1921 through 1937. But trying to sell this in the middle of the Depression, well, a concrete bridge salesman has difficulties. Okay, so that's what he did. Then along came a new, young, bright person called LACEY v. MURROW, and he was very capable and very persuasive. Politically, it was amazing. By the age of 28, he was the director of highways in the state of Washington. And from 1933 to 1948, he was chief engineer of what then became the Washington Transportation TBA. Well, anyway, whatever it is, it's the Toll Bridge Authority. And then under his direction, there were two major bridges started. The first, the original Tacoma Narrows Bridge, colloquially called Galloping Gertie. And then this bridge, the Lake Washington's floating bridge, the first one, colloquially called Gurgling Gertie. All right. He resigned his position from the Washington Transportation Authority, very propitious time, 2 months before the Narrows Bridge failure. And he entered the Air Force. He retired as a brigadier general and served extensively in combat in World War II and in the Korean War, and is now buried in Arlington Cemetery. He also has a famous brother, Edward R. Murrow, and there is he with his brother in World War II. So, Hadley introduced the concept of the concrete floating bridge to MURROW, and 3 months after MURROW had become head of the WTBA. The meeting lasted about 3 hours. MURROW quickly accepted the concept, and the preliminary design was completed 4 months later. The construction started 10 months later, and the bridge was finished 18 months later. Add those numbers up, and you get, I think, 32. 32 months less than 3 years from start to end. Now we argue about bridges in Washington State. If we build another concrete floating bridge, 10 years or something. Prior to the formation of the Washington Toll Bridge Authority, there'd been a Seattle Toll Bridge Authority, which had endorsed a $3.5 million concept to build a steel truss cantilever bridge across the narrowest point of the channel to the middle of Mercer Island. But this was not very good because it was a route that jogged all over the place then to get there. The straight route was much better. The Seattle Toll Bridge Authority considered the concrete pontoon but discarded it, with the newspapers labeling it as like scows chained together, and the environmental engineers deeming it a desecration of the lake and predicting it would ruin property values and sink within 5 years. After completion of the bridge in 1940, the newspapers declared it to be utterly amazing and the eighth wonder of the structural world. So much for newspapers. All right, so why a floating bridge? The location was the most direct route. The greatest depth to the foundation made tower construction very challenging. Because the lakes were controlled by locks, there was a regulated lake height and very little current, so that it made water-to-land transportation easily. The whole idea that the thing could be built within 2 years was amazing. And in 1935, the estimated costs were, for the floating bridge, $7 to 10 million. For a suspension bridge, 35 to 50 million. And in a tunnel, if they could build it, 50 to 100 million. That gives you some sort of ratio. So the concrete bridge was going to win out. The most recent concrete bridge we're building is estimated to cost 800 million. And why concrete? Why not wood or steel? Well, the dead load of concrete provides more inertia than a steel or wood floating bridge, and therefore more resistance to the weather conditions. This is the layout of the 1940 bridge. And it's hard to see. Seattle's on the right, Seattle's on the left, Mercer Island is on the right. You've got the profile of the lakes, and the key features are that it's a cellular pontoons with an integral roadway. We now build cellular pontoons but elevate the roadway above it on a separate structure. Each pontoon is anchored to the lake bottom transversely. You had to have an opening span for ships, and you had a challenge in building the transition spans to the land. And what the bridge consisted of was 19 pontoons bolted together. And the same concept we continue to use in the new bridges built today. So if we draw the critical elements, you have the pontoon in the middle, the little thing, and long anchor cables that go out. So the anchor offset is about 700 feet. And the anchor tension is typically 120,000 kips. So we're building another one of these, a cross-section of which is shown down there in the bottom. And if you look at where these anchors are going to be, they've dropped anchors down now, and the whole lake looks like massive lobster pots all the way across it, because they're going to pick up these things and thread those chains through afterwards. The pontoon dimensions, look at them, 1949, 358 feet long by 58 feet wide by 14 2/3 feet deep. Doesn't it remind you of a concrete ship from World War I? And then we have, in 2012, we've advanced a lot. We've gone 359.75 feet long. We're 75 feet wide, so a bit wider there. And we've gone 33 feet deep because we're putting so much more load on each one of those pontoons. We follow the same type of construction. On the left, we have the dry dock for the original construction, which was built in Harbour Island in Elliott Bay in May 1939. And on the right, we have the current dry dock for the construction of the pontoons in Aberdeen, Washington. Picture from February 2012, and we're building 6 pontoons at one time. On the left again, we have creating the bottom slab, it's called the keel slab, so we can get the things right, because it's like a ship, keel slab, and then pouring the interior walls. On the right, we have at the bottom how the top slab is being built, the deck slab in Aberdeen, and the interior walls, which are now precast in the pontoon in Aberdeen. The first construction was almost a continuous pour for the LACEY v. MURROW Bridge, the 1940. 36 hours was the time it took to pour the first pontoon. Always wheelbarrows dumped into the formwork. Now, it's so much deeper. It takes so much longer. And they do it in 6 different sections. We have to build these anchors. So out in the left, we see what was done in the 1940s. The pontoon is not nearly of the same depth, but you have to take this anchor and put it through the middle of the pontoon, which is the steel bit you see there, and then they're forming up the wall underneath that steel bit. And then you have to lower down the anchor into the water. They're now a little bit better about it. We have barges and cranes and everything else out on the lake doing it. One of the challenges is where you build it and then you have to transport it. In the 1939 one, we went from Elliott Bay, which is just in Puget Sound in Seattle, through the locks and down to where it says now Interstate 90. That was where the first bridge was built. Because we are trying to give an economic revival to Aberdeen, which is out on the coast, the new pontoons are being built there, and they have to be towed all around the coast, through the locks, and into the site. That's a 2-day tow. Of course, it also means that the pontoon spends quite a bit of time in salt water before it ever gets to the fresh water of Lake Washington. And that's why you don't want it to crack. All right. And then you have to get through the locks, which I said was 10,000 tons. You can see the 1939 pontoon going through the locks. And because it's not as wide, it has about 6 feet, 10 feet of clearance on either side of the locks. The current one going through had just 1 foot 6 inches of clearance on either side of the locks. And to retrofit the next ones coming through, we've had to post tension top and bottom in the transverse walls, reducing it to 6 inches either side. That one still has to come through the locks. It'll be interesting. They're then towed through the ship canal, and this is going past the University of Washington, the original pontoon with the roadway in place. Now we've got the pontoon for the new bridge sitting out on the lake without any roadway yet put on it. And much opportunities for restaurants. Here we see the 1940 bridge being assembled on the lake. They started in the middle of the lake and went either way. And when this bridge blew down in a storm while it was being retrofitted in 1990, the first pontoon was in the middle, and that was the first pontoon that was broke, the first one that was constructed. We had this problem of the opening span. You can see what difficulties the opening span creates. We've got rid of opening spans because that's where the biggest damage always occurs in each one of these bridges. Here's the opening day, July 2nd, 1940. A great accomplishment. Everybody was very happy. What we've got now is, this is the longest bridge, which is the State Route 520 Evergreen Point Bridge. The total length of the bridge is 12,404 feet. The floating length is 7,378 feet. The bridge has a much longer fetch, so it's regularly subject to strong winter storms. And it's rather a challenge driving across it in a strong winter storm because it's like a ship. and it rolls and throws water over your car and everything else, you know. The next one they did was to go to the Hood Canal, which is a salt thing, arm that comes off Puget Sound, off the Strait of Mandifuca, and half of that blew down in about 1980, and so they replaced it. So there was the west half, which was the remaining, and then they put in a new west half, sorry, got it around the wrong way. And then they replaced the east half, that's right. So down upstream of the Hood Canal Bridge is the Silverdale Trident submarine base. So they open this bridge, and there's a nuclear submarine, USS Ohio, going through the bridge. So another challenge, having allowance for nuclear submarines. Finally, this is what the LACEY v. MURROW Bridge has now become, the one that sank, the first one. There are two now. Homer Hadley, remember him? He was the guy with the idea. That's on the left. LACEY v. MURROW, the skipper, that's on the right. The total length is 9,559 feet. The floating length is 6,620 feet. And I'm glad to answer questions. Yes?
Do you have any problems with corrosion? Typically on a concrete bridge with piers, the tidal zone is kind of the worst area. It seems like this would be everywhere. Is that splashed up?
First of all, the bigger bridges are in Lake Washington, which is freshwater. Only the Hood Canal Bridge is in saltwater. Do we have corrosion problems? Yes. Are we worried about corrosion problems? Very much so. After that 2-day tow of the new pontoons, which unfortunately cracked at the ends in some positions, there's concern that the water has seeped into the crack and will attack the reinforcing guard. When the bridge, the original one, sank and we broke bits apart, it was amazing how good the original reinforcing bars still looked in that bridge.
Do you have to have bilge pumps in the pontoons? So you anticipate water to leak in and then you have to pump it out?
The original bridge had no bilge pumps. It had openings about 6 inches above the bottom, so water could flow from one cell to another. That proved to be deadly during the retrofit. The contractor doing it lost where he was putting water, because you were not allowed to take water out of Lake Washington or put water back into Lake Washington for environmental reasons. But because of noise reasons, they were told they had to do it by hydro demolition. So they were running pipes, both to bring water to and take water away from the job site to 2 miles almost to the shore. Now this created a difficulty, and you might understand why the contractor lost control of where he was putting water. So bilge pumps, not in the original bridges. Now there's a very complicated system of hatchways like it's in a ship. The water has to get up to at least 3/4 of the height in the cell before it can go to the next cell or flow over. And there's a very intricate system of measuring whatever is the water depth in each one of the cells, and an alarm system in the maintenance office back on the shore.